Okay, I'm going to do for you in this video a question from your assignment number 7, which was on the wind distribution, and it's question number 6. So we have a wind turbine, rotor diameter 55 meters. We don't actually need that here. Rated at 1 megawatt, so the rated power, P rated, is 1 megawatt. And it's rated wind speed, so that's U R, 14 meters per second. Cut in speed, UCI for cut in is 4, and cut out, UCO, is 25. And we have a Rayleigh distribution with a mean wind speed, so that's U bar, of 10 meters per second. Okay, we want to calculate the probability that the wind is going to be less than the cut-in and that the wind is going to be greater than the cut-in, and then we want to know about its energy production in a year based on that rated power. So the first thing is recall the Rayleigh distribution. So the Rayleigh distribution is a probability distribution of wind speed. It's not a normal distribution, it's a little bit skewed toward the higher end of wind speed. So U is the wind speed on the x-axis, and on the y-axis is the probability that the wind speed will be a certain value per meter per second. Okay, now the average is not at the peak. The average is right around here, U bar. U cut in would be way over here, so that would be the 4, and then U cut out would be way over here. Okay, now the area under this curve represents probability. So the area equals the probability that wind speed has a certain value. Now usually the way we do it, if we're going to do an area, is that we calculate the probability that wind speed would be greater than a certain value. So probably that wind speed is greater than U prime. And the equation for that, which this would be an equation on your equation sheet. And so the probability that U is greater than U prime, if you have a Rayleigh distribution, is equal to E to the negative pi over 4 U prime divided by U bar squared, and that's it. That's a probability. So the beauty of this distribution is that all you need to know is the average wind speed U bar, and you can calculate these probabilities. Okay, so let's calculate the probability that the wind speed is going to be greater than 25. So what you're actually doing is you're calculating the tail end area. What is this area here? This would be phi U greater than 25. Okay, so the probability that the wind speed is greater than 25 meters per second is just E to the minus pi over 4, 25 over 10, the mean wind speed's 10, squared. And that probability works out to be 0.0074. So it means that there's only a 0.74% chance the wind is going to be blowing stronger than 25. The number of hours in a year is equal to 8,760. And so if 0.74% of the time the wind is greater than 25 meters per second, it means the number of hours that wind is greater than 25 meters per second would be the 8,760 hours per year times the 0.0074. So it turns out that there are only 64.7 hours in a year where you have to shut this wind turbine down because it's too windy. Okay. And similarly, if we want to know how many hours the wind is greater than the cut-in for, so what you'd be calculating there you'd be calculating this. It'd be a big number because you're going to calculate this whole area here, from here all the way out to the tail. And you can see, if you want to know what it is between the cut in and the cut out, you have to subtract the two results. Okay, so for greater than 4, the probability that the wind is greater than 4 meters per second, you just put 4 into that formula. E to the minus pi over 4, 4 over 10 squared, and you get quite a high probability. It's 88.19. So 88.2% of the time the wind is greater than 4. So that means you're going to be able to use the turbine. There's no point in running it if the wind speed's less than 4, because that just wears out the bearings. Okay, so that's a greater than. If we want less than, then we have to take 1 minus 0.8819. And this is if it's less than, and this is only 0.1181. So the number of hours wind is less than 4, that's the cut in, 0.1181 times 8760, and that gives you 1,035 hours in a year. Okay, so that's part A and part B. Now it's talking about the rated wind speed. So remember the graph that we did in class, where you have power versus wind speed, and the curve looks sort of like this. Okay, this is your cut in. This is your rated wind speed. And for this machine it's 14. And then this is your cut out. This is your 25. And so if we want to know how much energy this turbine is producing, we need to know how many hours is the wind speed between 14 and 25, because basically this is the production region, and that's the only region that you count here. So we need to know what's the probability that the wind speed is greater than 14. So we just pop that into the formula, pi over 4, 14 over 10 squared, and we find that that's about 21% of the time, so 0.2145. And so the number of hours that it's greater than 14 is multiplied by 8760, and you get 1,879 hours per year that the wind is greater than 14. Now remember, we have to subtract those few hours where it's too windy, where it's greater than 25. So the number of hours between 14 and 25 would be the 1879 hours per year minus the 64.7, because that's when it's too windy. And so the number of hours that we have producing power for its rated wind speed is 1814 hours per year. Okay, so, and it says that at that rated power up here, this number would be 1 megawatt. And so the energy produced would be power times time. And so the power is 1 megawatt. That's 1,000 kilowatts times 1,814 hours per year. And so then that gives you 1.81 times 10 to the 6 kilowatt hours. That's energy per year. And that's the final answer.